Hello everyone, welcome back to my channel. My name is Chinmaya SCT from Sri Venkateswara College of Engineering from the branch of Information Science and Engineering. In this video, I am going to tell about Lagrange's theorem from the subject of discrete mathematical structures. Lagrange's theorem. It is a fundamental result in a group theory. It relates the order of a subgroup to the order of the entire group. The theorem is named after the mathematician Joseph Louis Lagrange. Key definitions. A group is a set equipped with an operation satisfying specific axioms. The order of a group is the number of elements in it. It is a subset. A subgroup is a subset of a group that itself forms a group under the same operation. Statement of Lagrange's theorem. It states that the order of a subgroup divides the order of the group. If G is a finite group and H is a subgroup, then order of H divides the order of G. This has important implication for the structure of groups. Notation. The notation of order of G represents the order of the group of G. The notation order of H represents the order of the subgroup of H. Understanding this notation is crucial for applying Lagrange's theorem. Examples of groups. The group of integers under addition is an example of an finite group. The symmetric group S of n Sn consists of all permutations of n elements. Finite groups such as the cyclic groups illustrate Lagrange's theorem effectively. Cyclic groups. It is generated by a single element. The order of a cyclic group is equal to the number of distinct powers of the generator. Lagrange's theorem applies directly to cyclic groups, showing their subgroup orders. Applications of Lagrange's theorem. It helps determine possible order of subgroups. It can be used to prove that a group cannot have a subgroup of a certain order. The theorem is essential in classifying finite groups. Consequences of Lagrange's theorem. One consequence is that every group of a prime order is cyclic. It implies that a group cannot have a subgroup of order 6 if the group order is 5. The theorem also leads to the concept of cosets. Cosets and their importance. A left coset of H in G is formed by multiplying all elements of H by an element of small g from capital G. Cosets partition the group into distinct non-overlapping subsets. The number of distinct cosets corresponds to the index of the subgroup. Index of a subgroup. The index of a subgroup H divides in G is the number of cosets of H in G. It is denoted as G of H. Lagrange's theorem states that G, the range of G is equal to range of H times G of H. Proof for outline of Lagrange's theorem. The proof relies on partitioning the group into distinct cosets. Each coset has the same number of elements as the subgroup H. The number of cosets multiplied by the size of each coset equals the size of the group. Applications in group theory. It is used to analyze the structure of groups. It assists in determining normal subgroups and simple groups. The theorem is fundamental in the classification of finite groups. Limitations of Lagrange's theorem. The theorem only applies to finite groups and subgroups. It does not provide information about the structure of the group itself. The existence of a subgroup of a particular order is not guaranteed. Related theorems. The silo theorems extend the ideas of Lagrange's theorem. They provide conditions under which subgroups of certain orders exist. These theorems are critical in finite group theory. Historical context. It was established in the 18th century. It was a part of the early development of a subgroup theory. The theorem laid the groundwork for modern algebraic structures. Examples in practice. For the symmetric group S3, which has an order of 6 subgroups, can be order of 1, 2 or 3. Cyclic group math a subset of Z by 5. Math has a subgroup of order of 1 and 5. These examples illustrate the applicability of Lagrange's theorem. Visual representation. Diagrams can illustrate the cosets of a subgroup within a group. Visualization aids in understanding the structure of groups and subgroups. Graphical representations enhance comprehension of Lagrange's theorem. Further reading. For deeper understanding, explore texts on abstract algebra. Topics may include group theory, cosets, and normal subgroups. Many online resources provide tutorials and examples of Lagrange's theorem. Summary of this video and presentation is the Lagrange's theorem connects the order of the groups and their subgroups. It is a foundational result in group theory with significant implications. Understanding the theorem is essential for studying advanced algebra. Conclusion. Lagrange's theorem remains a pillar of modern mathematics. It Its applications extend beyond pure group theory to various fields. Mastery of the Theorem enhances one's mathematical toolkit. This outline provides a comprehensive overview of languages theorem, structured for a presentation format with a clear sub-bullets for each slide. Thank you.